In this section, we're going to review some properties of exponents and then scientific notation. Let's begin with the exponents. One thing I want to draw our attention to here is in these examples, the b that we see listed here, 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 all of these b's are just standing in the place of any real number. And if we have a b here and a b here, it's implied that even though this b could be any real number, whatever it is here is the same that it is here. So for instance, this could be written as our example if we were looking at 3 to the second times 3 to the fifth. Following this notation, the b is taking the place by the 3. The m is acting like the 2. The n is acting like the 5. So just so we can kind of get an idea there. So the way I would read this is some base to an exponent times the same base to a different exponent can be simplified by keeping the same base, but by adding the exponents. So in this case, 3 squared times 3 to the fifth is the same as 3 to the 2 plus 5, which could be simplified as 3 to the seventh. Now if we have a base to a certain exponent raised to another exponent, in that case what you do is you keep the same base, but you multiply the exponents. So an example of that could be 3 squared raised to the fifth power. In this case we've got an exponent raised to another exponent. So the exponents combine through multiplication, and this would become 3 to the 10th. If you have the same base to some exponent divided by the same base to another exponent, then you keep the same base, but you subtract the exponents, and since subtraction is involved, order of subtraction matters, so you always take the top exponent and subtract away the bottom exponent, so we would get m minus n. So 3 squared divided by 3 to the fifth would be 3 to the 2 minus 5. 2 minus 5 is negative 3, so this would simplify to 3 to the negative 3. Now we want to remember any base to the 0 power takes on the value 1. So even if we had something like 1234, if that's all raised to the 0, that's the value 1. One word of caution, if we had negative 1, 2, 3, 4 raised to the 0, that's going to be different than if it had been written as negative 1, 2, 3, 4 all in parentheses. In this case, we're raising the whole value to the 0 exponent. Anything to the 0 is 1, so that becomes 1. But in this case, whenever there's no parentheses written, it's implied that you're actually only raising the first term to the 0, and then you're applying the negative, even if those parentheses aren't written. By the fact that there's no parentheses written in this problem, it would be implied that you would just take the 1, 2, 3, 4 to the 0 first, which would give a 1 there, but you still have the negative out in front. So if we wanted to raise the whole thing to the 0 power, we'd have to offset that in parentheses to begin with. Finally, if you've got some base raised to a negative exponent, then you can rewrite that as 1 over the same base, but to the positive version of the exponent. So for instance, 3 to the negative 5 is equal to 1 over 3 to the fifth power. So based on the properties we just looked at, let's simplify the following. I'd like to give everybody a moment to attempt these first 3 on their own, looking back at our properties that we just talked about. So why don't you take a moment to pause the video, and actually let's attempt the first 4 on our own, and then unpause when you're ready to check your work. For our first example, we have the same base to an exponent times the same base to an exponent. So in this case, we know that the exponents can combine by being added. So that's 2 to the 5 plus 3 as the exponent, which could be simplified as 2 to the 8. Now in our next one, we have some base 4 raised to the second power, and then raised again to the third power. So that's an exponent of an exponent. You keep the base the same, and then you multiply the exponents. So that would simplify as 4 to the 6th. Now in our next example we have same base to some power divided by same base to some power. In this case the exponents subtract in the proper order, top exponent minus bottom. That would leave us with 5 squared. Any number to the 0 is equal to the value of 1. And here we have our caution. Notice 7 to the 0 is 1, but negative 3 to the 0, that would be the same as writing negative 3 to the 0. Because unless we intentionally begin with the negative 3 all in parentheses, we are to assume that you raise 3 to the 0 power first and then apply the negative. Now 3 to the 0 is 1, so that would leave us with negative 1, and we would get negative 1 as our answer there. Here we've got 4 to a negative power. We know we can rewrite any base to a negative exponent by 1 over that base to the positive version of the exponent. So that's just a quick review of some of these exponent properties. I recommend you start working on these homework problems as well. They're assigned at the end of this section. This will just help practice knowing when to apply each property. Next we'll review scientific notation. Now scientific notation is very useful in either expressing very large numbers or very small numbers. So let's look at the formatting of scientific notation. Scientific notation always looks something like this, where A is a number greater than or equal to 1, but it should be less than 10. So A lies between 1 and 10. And then we write the times symbol, so we always write the times symbol for our multiplication, 10 to some exponent n, where n is guaranteed to be some integer. But remember, integers can be positive, negative, or 0. Now, if n is negative, that means that you would, in order to turn it from scientific notation into our regular decimal notation, you would move the decimal place in A to the left the absolute value of n places. If n is positive, then you move the decimal point in A to the right n places. And I think this is a lot easier to see in practice than to say in words, so let's start with our first example. We know both of these are in scientific notation. In our first example, our A is 1.275. In the second example, the A is taking on the value 1.1. In the first example, the n is 10, this exponent. In the second example, the n is negative 4. So we can kind of see how this notation is used below. And we're asked to write each expression in decimal notation. Think of decimal notation as our normal numbers. No longer in scientific notation. So in this case, we notice the exponent on the 10 is positive. So what I would do is I would write out the A part, the thing that comes in front, write it down. And then since it's positive, I should be getting to be a bigger number. That means I should be moving to the right. And we can kind of use our intuition on that. Whenever the exponent is positive, this is going to be a value greater than or equal to 10 at least. In this case, it's much greater. So multiplying by something 10 or greater is just going to get you to be a larger and larger number, which helps us remember we go to the right. So what I would do is I would find the decimal place. If one's not written, it's implied to be to the right of the last number. And in this case, since our exponent is 10, we move over 10 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put my decimal point there, and every blank where there's something missing, I add in a 0. So writing this out, I would get 1, 2, 7, 5, followed by 1, 2, 3, 4, 5, 6, 7 zeros. So this number, 1.25 times 10 to the 10, actually represents this value. Now for the next one, we see our value of A is 1.1, but as I think of moving decimal place, I notice the exponent is negative 4, so I should be moving 4 places to the left. Why don't you take a moment to pause the video and attempt this on your own. unpause to check your work. So as I'm moving to the left, because it's a negative exponent, we are going over 1, 2, 3, 4. 0 in every empty place, and this would be equal to the value 0.00011 in decimal form. So we just saw how to go from scientific notation to decimal form, and we're also going to learn how to do the reverse, how to go from a decimal to scientific notation. We'll talk through the steps here, but then we'll see it in our example. First, you need to determine a, which is the numerical factor in the front. The way you would find that is you would move the decimal place in order to get a value that is between 1 and 10. Now you keep track of how many places you had to move it, and that's going to be our in, the exponent on the 10. And if we had to move to the left, the exponent would be positive, and if we had to move to the right in this exchange, going from decimal to scientific notation, the exponent would be negative. Let's work through our first example. So in this case, you have to spot the decimal place, and if there's not one written, it's implied to be to the right of the last digit. And now this is a number definitely not between 1 and 10, but we need to move the decimal place and keep track of our movements until it looks like a number between 1 and 10. So we'd go over 1, 2, 3, 4, 5, 6. We had to move over 6 decimal places before it looked like 4.6, which is a number between 1 and 10. So we would write 4.6, always the times 10, and the exponent is how many places you had to move. In our case, we had to move over 6. And the good news is you could always take this in scientific notation and turn it back into a decimal to check your work. Now in the next case, we are taking our decimal point and we're moving it over until we get a number between 1 and 10. So that's 1, 2, 3, 4, 5. And that would leave us with 2.3, our times symbol, 10 to the, since we had to move over to the right, that's going to be a negative 5 in this direction because we are taking a very small number and making it look larger, but it's not really 2.3. It's 2.3 after you move the decimal places. You then have to move it 5 places back to the left to get back where you started. So when you start with the bigger number, and then the a looks smaller, that's when the exponent is positive. But when you start with a smaller number and then the a looks bigger than that, that's when the exponent is negative. Now in this example, we've got just a small word problem. As of January 2016, the population in the United States was approximately 322 million. Express this in scientific notation. To do this, I would first say we need to be able to express what is 322 million just in terms of digits. That's going to be equal to 3, 2, 2, and a million has 6 digits, so it would be followed with 6 threes. Now to write this in scientific notation, you first find the decimal point. Remember, if one's not written, it's implied to be to the right of the largest, or sorry, the farthest right. So we go all the way to the end of the value, and then we move over 1, 2, 3, 4, 5, 6. Again, we have to keep moving because that would just leave us with 322, and we need to be between 1 and 10. So we go over 7, that's at 32, not good enough, 8. And now 3.22 is between 1 and 10, so we went over 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 3.22, our times symbol, 10 to the 8th, is another way of expressing 322 million. Now there's just a little bit more to cover. We need to talk about how could we multiply numbers in scientific notation and how could we divide numbers in scientific notation. And when you're multiplying numbers in scientific notation, just think about like things multiplied together. So the digits get multiplied by the digits, and then after that's done, the exponents get multiplied by the exponents. And in order for us to see this a little bit more readily, I recommend that since multiplication, the order of multiplication doesn't matter, we could rewrite this as 3.4 times 2 times 10 to the 9th times 10 to the negative 5th. Now this we can just check in our calculator. That would be 6.8. And here we're going to use our rule of exponents that we started this section with. So since we've got the same base, you would add the exponents, so 9 plus -5th, that would give us 6.8 times 10 to the positive 4. And that would be the value of those two numbers when multiplied in scientific notation. Next, when dividing things, you divide like terms. And I recommend in this case splitting up the fraction into two pieces. Since this is multiplication, you can split the fraction across multiplication. So this is the same as 8.4 divided by 4, all times 10 to the -7 divided by 10 to the -4. So in this case, we do 8.4 divided by 4 in our calculator, and we would get 2.1. Here, since we've got the same base 10, but we're dividing this, 10 to the -7 divided by 10 to the -4, we would subtract the exponent, so that would give us times 10 to the -7 minus -4. Now here we need to be cautious whenever we're subtracting a negative. That's the same as adding that term as a positive, so that's 10 to the -7 plus 4, which would simplify to 2.1 times 10 to the -3. So when multiplying and dividing scientific numbers, just think like things together. Like things divided in this case, or in our previous case, like things multiplied. And then our properties of exponents. Now why don't you take a moment and pause the video and read through our next example and think about what operation do you think would be useful to us to answer the question. So pause the video now and read through this. So here we had the national debt was 8.9 trillion, which they nicely wrote out for us in terms of scientific notation. At the time there was approximately 322 million people, or in scientific notation this. If the national debt was evenly distributed among every citizen, or every individual of the United States, how much would each citizen have to pay? So whenever we think about evenly divided, if you've got a lot of things and you're splitting it into equal shares, that's the idea of division, right? So what are we splitting into equal shares? We're taking the national debt and splitting it into this many shares, which would mean that this problem really boils down to taking the national debt and dividing that by the amount of people we're distributing it to in this example. Now we know like things go together, number divided by number, this by this, so I could rewrite that as a fraction to help me see it. Simplify each piece. And let's just round this to a few decimal places. We'll round it to 1, 2, 3, 4 decimal places. That's going to give us about 5.8696 when rounded, times, in this case, you would subtract the exponents because they're being divided. And that's our answer in scientific notation. And just for practice, why don't you write this in decimal form? So turn this scientific notation into decimal form. Pause the video while you attempt that. Remember, you start with the value in front of the multiplication, and it says move it the decimal 4 places since it's positive to the right. So we had 8696. But we're moving 4 decimal places to the right, so 1, 2, 3, 4. So that would be the national debt per individual, if we spread it around based on these previous population, would be about $58,696 per individual to account for that. And notice whenever we can use scientific notation, we can work at thinking about just how many ways can we split $18.9 trillion, which without scientific notation, it would be very hard to conceive of $18.9 trillion. But with scientific notation, we can write that as just 18.9 times 10 to the 12. So at the end of each section, remember we do have our homework problems listed. I recommend highly that you attempt these as soon as possible, checking your answer after each problem and seeking help if you have questions about a problem. You can always reach me through virtual office hours or Canvas message or PSC email.